right, let's talk about universal gravitation. So this is the idea that every object with mass attracts every other object with mass. So I'm going to put that on the board. Every mass attracts every other mass. Now, this idea isn't necessarily new. We've talked about gravity in the context of gravitational acceleration, which is how fast we're going to fall here on Earth, 9.8 meters per second squared. We've talked about the fact that the force of the Earth pulling on us is our force due to gravity, otherwise known as our weight, and that amount is our mass times that gravitational acceleration, 9.8. We also talked about the fact that for every action, there's an equal and opposite reaction. So Newton's third law is saying there that if the Earth is pulling on me, I must also be pulling on the Earth. And that's really where this idea comes from. Newton expanded his idea of gravity. He's like, well, it's not just that every object that I can see is falling to the ground. It's that every object on the whole entire planet, and probably in the whole entire universe, is being pulled on by some other object. His third law says that if it's being pulled on by some other mass, then that object must also be pulling on the other mass. It's an equal and opposite reaction there. So every object is pulling on every other object. That's the idea of gravity. Now, in our context here on Earth, the only thing that really matters is the Earth. It's our very largest, nearest thing. And so the gravitational force from all the other objects, right? In theory, the iPad I'm recording this on is pulling on me and I'm pulling on it. But those numbers are so incredibly tiny that it just doesn't show up in our daily movement and our daily physics that we see. So every object around you is being pulled on by you, and it's pulling on you. The reason we only see the effects from the force due to gravity of the Earth is because it's the only thing large enough for us to really see this. So he wanted to really define this force due to gravity, this attraction between every single mass. He wanted to figure out what the relationship was between that force due to gravity, or the gravitational acceleration, and some other things that might affect it. So he knows mass is involved, that's guaranteed. He's fairly certain that the distance that things are apart from each other might matter. And so he starts testing this. He wants to compare the gravitational acceleration here on Earth, which is 9.8 meters per second squared, to how much the Earth is pulling on some other object. He needs a nearby object that Earth is clearly pulling on and making orbit our planet. So yeah, you guessed it, it's the moon. It was handy because we knew a lot about the moon. We had been studying the moon for a really long time because there wasn't electricity. So at nighttime, what did you do? You looked at the moon and the stars in the sky. So G of the moon, we wanted to figure out. Now we can do this. We know physics. So the moon is out in space. The only force acting on it is Fg moon. That's the force due to gravity at the moon. So its F net would be that it's definitely accelerating because it's going in a circle. Yeah, going in a circle. Definitely accelerating. And it's m times the gravitational acceleration at the moon. We don't know what that is. It's not 9.8. Remember, gravity doesn't disappear above the Earth when we get out of the atmosphere. It's a little bit smaller, but not by much. But as I go up in height, as I get further from the center of the Earth, it does decrease. So out by the moon, it's got to be something else. It's not 9.8, right? So to figure that out, they said, well, it's moving in a circle. V squared over R is equal to G moon. And they found that G moon, the gravitational acceleration at the moon, was 0.00272. You're like, how is that enough to get the moon to orbit the Earth? Remember, it's the only force. It's unbalanced. It can do mighty, mighty things. So the gravitational acceleration at the moon is 0.00272. So that works out to be about 1/3600th of our gravitational acceleration here on Earth. That's a pretty cool number. It's a nice round-ish number. Let's see if we can go find other similar numbers. So if that's the gravitational acceleration at the moon, he had this idea that distance mattered. So he then went and compared the radius of how far the moon is away from the center of the Earth to the radius of the Earth. And when he did that, he figured out the proportion there was 60. The moon's radius is 60 times that of the Earth's radius. Well, that cannot be a coincidence, he said. He was like, looky there. It turns out that the gravitational acceleration is proportional to the radius squared. So he came up with this. Gravitational acceleration is proportional, that symbol means proportional, to 1 over the radius squared. We can see this. This is radius, 60. The proportion of the radius is 60. This is 1 over 60 squared. So gravitational acceleration is proportional to 1 over radius squared. This is how he developed his equation for universal gravitation. The force due to gravity of an object is equal to G m1 m2 over r squared. This right here is the 1 over r squared relationship he found. After that, he knew the masses had to be involved, so he's got both masses. Remember, every mass is pulling in equal amounts on every other mass. And then he had this constant. He didn't know what the value of that was. He didn't know all the masses of the things in the universe, and it was kind of hard to figure out, so he died without knowing this number. We did not have to do that, though. G is equal to 6.676 times 10 to the negative 11. So we do know that. That is on your equation sheet. Now, if you end up taking electricity, you're going to find out that this looks very similar to Coulomb's law. That is a really cool thing about physics that we can get into on another day. But for today, all we care about is that this is the equation for the gravitational force between any two masses. Doesn't matter what they are, any two masses. If you plug in U and the Earth and the radius of the Earth, you will get your weight. This is the force due to gravity of any mass pulling on any other mass. Now, we know that Fg can be rewritten as mg. This would be one of the masses, right? One of the masses that's pulling on each other. So if we cancel this out, we get that the gravitational acceleration is equal to our gravitational constant times whatever large mass is nearby causing this gravity divided by the radius, how far you are away from it, squared. So this is how we get 9.8, okay? This is our gravitational acceleration. We take the G constant, multiply it by the mass of the Earth, divided by the radius of the Earth, and we will get 9.8, okay? So if we want force, we use the full equation. If we just want gravitational acceleration, that's a long word, then we're going to cancel out our mass, or the mass of the object we're talking about, and we get this smaller equation here. Okay? Now I want to make one more comment about this. One thing that we learned, I mentioned just a second ago, that this equation looks like something in electricity. Electrostatic forces were the other long-range force. Remember, gravity is the only force that doesn't require you to be touching the object, right? A spring, a string with tension, a normal force with the surface, friction with the surface, all of those are contact forces. You have to be touching for them to work. Gravity was always the oddball, where we're not currently touching the center of the Earth, but it's acting on us. The same thing worked in electricity, and so they decided that what actually happens in electricity is that charges create these fields. They change the whole area around the charge, and as another charge comes nearby, it reacts to that change. So it's not that each charge has to touch each other to apply a force, it's that this charge disturbed the whole area, and when another charge showed up, it feels that disturbance. That's the idea of a field, okay? One object creates this field, and another object can feel a force because of that field. So in gravity, a little bit past Newton, we also decided that gravity must work like a field. So every mass acts as a gravitational, right, change to the space and time around it, creating some sort of gravitational field. All you need to know about that is that the gravitational field strength is the same thing as this G here. So it's our gravitational acceleration and is also the gravitational field strength. We're not going to talk about it in any more depth than that, but when they comment and say gravitational field strength, it's the same thing as G. Okay, so with these two equations, you can solve for things like, hey, what's the force of Jupiter on Pluto? What's the force of the sun on the moon, right? Any two masses that they can name, you can figure out what the force due to gravity is acting on them, or you can figure out the gravitational field strength or gravitational acceleration of those two objects, okay? That's what these are used for, all right? Last thing here, let's talk about our solar system. I love our solar system. I've been living in it for my whole life, you know, never left the solar system. I really think it's homey, you know, it's the only one that screams life. All the other ones I'm not so sure about. So this is the solar system for me. And in this solar system, if we say that FG is equal to GM1, our big solar system is all revolving around a big mass of the sun. And then this R would be the radius of something around the sun. Now, that force due to gravity for the Earth, for Venus, Mars, all the planets, leads to us orbiting the sun, right? That's what happens. Now, those orbits, for the most part, can be approximated as circular. Some of the planets do it better than others. Pluto lost being a planet because it did it so poorly. Its orbit was so not circular that we really couldn't make this approximation. But for most of the planets, we can approximate that this force leads to an acceleration. That acceleration is a centripetal one that leads us to go in a rough circle. Now, if this is the mass of the Earth, and this is the mass of the Earth, those cancel out. Maybe it's the mass of the moon, not the moon, Venus or Saturn or Jupiter, whatever planet it might be. I get this relationship, V squared over R is equal to G M sun over R squared. Now I'm going to take this one step further. We know that V is 2 pi R over T squared. R is equal to G M sun over R squared. Whoop. Let's keep canceling things out. The algebra here is looking yucky, but let's keep playing. So I get 4 pi squared R squared over T squared times 1 over R is equal to G M sun over R squared. Oh my gosh, so many R's. All right, cancel those guys out. I get 4 pi squared over T squared R is equal to G M sun over R squared. Why are you doing this, Miss Slimer? Well, let me tell you something. For every single planet in our solar system, the number 4 stays the same because it's a number 4. Pi squared is going to stay the same because it's the number pi squared. G is a constant. Oh, I erased it, but 6.67 times 10 to the negative 11th. The mass of the sun is constant. So if I take all these things that are constant for every planet in our universe, or in our solar system, not universe, and move them to one side, let's see what happens. So I'm going to move all of those to one side, and that gives me R cubed over T squared is equal to G M sun over 4 pi squared. Now, the cool thing about this is that constant, 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 constant. Everything on this side of the equation stays the same for every planet in our solar system. The orbit for every planet in our solar system is roughly circular and is defined by this amount, which stays the same for every single planet. This led to a guy named Kepler's third law. Kepler's third law says that the proportion of the radius cubed over the period of circulation, so how long it takes us to do one full orbit around the sun, that's a year, squared, must be the same for every planet in the solar system. That's what Kepler's third law says. It says that for every planet in the solar system, all of this stuff over here is the same. So the radius cubed over t squared must be equal for every single planet. So this helped us figure out what some of the information about various planets were. We want to know their location. Well, we figured out what their orbital period was, and we compared it to our own. And this is how early astronomers were able to figure out a lot of things about the universe. Now, this would hold for any solar system, or maybe different solar systems orbiting a galaxy, anything like that. We're probably going to only use it in the context of our one solar system, or like a planet X and a planet Y. But this is Kepler's third law. It says that any planets orbiting a star inside of a solar system are going to have the same radius cubed over t squared proportion. And that is universal gravitation.